if that actually goes. Okay. So you guys are aware. I have no problems. If anybody has questions during, feel free to let me know. We can discuss different topics. I know sometimes it's easier to get questions addressed when you see it rather than trying to remember and come back to it. So feel free to let me know if you have any questions at any point. Basically, what I'll be talking about today is a lot of non-destructive evaluation, particularly microscale results. We know that a lot of the material behavior stems from how the microstructure is going to respond to whatever loading we do. So if we can find some way to monitor that, to understand that, and then link that to the scale of macro scale that we're using, it becomes a little bit easier for us to figure out what's going on and to predict the behavior and make changes. So starting with my team currently, 4 major students that are working directly with me, and then we have the Center for Advanced Materials Processing camp that we have additional colleagues working on different projects as well. I am in the process of recruiting a couple PhD students that will hopefully be joining us in the fall, but I haven't put them here yet because they haven't officially agreed to join. Sponsors for the projects that you'll be seeing. There's a lot of work that we do with the Department of Defense, particularly Air Force Research Lab and Defense Logistics Agency. You'll see a couple projects from them. You'll also see a project from DOE for coal materials. And then as far as the rest of this, Sandia National Labs I've done some work with in the past. So some of the results you'll be seeing come from that. And DuPont, same thing. I have an example of some of the work we've done in the past from them as to how we're leveraging this for advanced manufacturing processes. MRL is one of our local groups that does a lot of 3D printing. We have in-house a laser powder bed fusion system, but it's only one system, so it's kind of limiting in how much we can print. So we do work a lot with MRL, Material Research Lab, in order to expedite and allow us to test more things. And then TRI also I have here in the center. That is a non-destructive company. They do predominantly ultrasonic testing. And we're working on a pretty cool project. I will share as much as I can. We do have an NDA, so I can't share everything and all of the most recent results, but I can at least give you an idea of where we're going with that to see if you guys are interested there. So the talk I'm giving, starting with motivation about why I'm kind of doing the work I'm doing, the approach I'm taking to doing it, some of the results, and you'll see some of these results aren't actually directly related to manufacturing. They're more material specific, but how we're going to try to leverage the information in our manufacturing monitoring processes to see how things go and give you a little bit of a future work examples, kind of a system that we're working on now, as well as the conclusion of how all this kind of ties together. So the first thing is understanding what structure is. And structure is multi-scale. And we have to realize that it goes from bridges, large-scale structures, automobiles, aircraft, down to the microstructure. There's also the concept of health, structural health monitoring. How do we address whether or not something is good? A lot of the times that's done, but people ignore the initial structure. What defects might exist from the process of manufacturing itself that will affect the results. So something to keep in mind. And then another term that I'm leveraging quite heavily is IoT. Internet of Things, mechatronics, connection of electrical systems and mechanical systems. There are many terms I've heard for this. Ultimately, it's us trying to leverage as much as we can knowledge of mechanical systems as well as electrical interfaces to improve the results we can obtain, to make things easier. If we're talking about advanced manufacturing, that's everywhere. We can't ignore that. So we're talking a little bit about all of this. So again, focus is understanding material behavior. So if I want to understand the structure of the wing, understand this gear that I'm producing, I have to remind myself that as we zoom in, we're talking about a microstructure. A different microstructure will produce different results. That's given. So if we can control the microstructure, if we can understand the microstructure, we have the benefit then of improving the material properties to be something we may want. We can tailor the structure. We can alter it. Some of the ways that we commonly do this now is in the manufacturing process we do. We do a rolling process. It's going to alter the microstructure. In the case of a cold rolling in particular, it's going to cause us to have elongated grains in one direction. That's useful in sheet. Not so useful in a bulk, large structure that you want isotropic properties. But we can control that. We can even go so far in some concepts that we can actually, in cement, induce cellulose. We can add different elements at different scales in order to change the properties. Most of the time, there is some thought behind this as to why we would do this, but we don't really know what's going to happen until we try it and test it. We can guess, but we don't really know. So part of the question becomes, can we monitor what's happening in order to figure out what's going to be the result before we actually have to build and test all of these components? And that leads us to this figure that I use all of the time from McDowell, showing the concept that materials are multi-scale. We're talking, if we want to understand macro scale behavior, we have to understand what's happening at the subscales that lead to that. That means we have to figure out what scale are we actually going to test at? What are we actually looking for? The questions being, what are we monitoring? What are we looking for? How fast do we have to be able to monitor this? Can I take an image a second? Or is this a very fast process that happens instantaneously and I need something way more advanced? What scale is it happening to know whether or not I need a microscope or I can get away with a standard camera? And then where am I going to look for these things? So how do we kind of figure that out? How do we start working with that? The approach I'm using leverages microscopy, standard EBSD, scanning electron microscope, optical imaging, basically anything, any way you can think of to get an image of what the microstructure looks like, combined with non-destructive evaluation tools. In particular, you'll see I'll be focusing a lot on DIC, which is digital image correlation, the idea that we can generate strain maps simply by taking a sequence of images on a sample that has sufficient contrast that you can track that motion. All we're doing is tracking motion. And we're doing this with a system that looks something like this, that's got a stereo system, 2 cameras. That means we can actually generate the entire strain tensor for this material system as it undergoes deformation. All in plane and out of plane strains, which is very helpful. This particular one that you're seeing is actually a composite material that we are tensile loading, and you can see strain concentrations appearing as the fibers start to disbond from the polymer matrix. So the top layer is actually oriented 45 degrees. The second method I use a lot is acoustic emission. And this one you will see I use the most. There's a reason for this. DIC is powerful. It gives us a lot of useful information, but you can only see a surface. So if the damage isn't happening on the surface, or at least near enough that it affects the surface, you're not really going to see a change in your DIC results. Acoustic emission, on the other hand, is a passive technique. It's basically what you guys are doing right now. We're just listening for a change. That change can happen anywhere in the volume. And so long as the material is conductive enough that the wave can reach the sensor, we detect it. That means we can see damage that happens below the surface. And that is extremely helpful if we're trying to understand what's happening in manufacturing processes. A lot of the defects that occur will happen below the surface. And you won't see them if you don't have some method that allows you to probe there. And that leads me to X-rays, which is always helpful if you're trying to prove that something did indeed happen below the surface. It's very nice to actually be able to see below the surface to validate it's there. So what I generally am proposing is that the idea that we use these NDE tools to tell us what's happening. To do that, we have to make a connection to the structure. Essentially, we monitor the material, we see what's happening, we see the changes, we see the microscopy, we connect it to the load that we're applying, and we link that to the damage. From there, we can start to do a lot of cool things. For example, we can start combining techniques, DIC and AE together, surface information with volumetric information to see how things evolve over time. We can start delving into the acoustic emission, and instead of just looking at a single waveform or this representation of dots, we can start to extract features that describe it. Those features can then be leveraged in machine learning outcomes to determine whether or not we have damage. In this particular example, we're talking about aluminum monotonic and fatigue testings that this method was developed for. The emphasis I want to make is that those defects that we found in testing produce the same type of waveforms that the defects that will happen during manufacturing processes produce. So this is one method for us to start to build a training set of data for us to leverage in machine learning if we want to do some more advanced manufacturing type applications. That being said, all of that requires a lot of user interaction. And if we want to really move into this understanding and get a lot of detail, we need to try to find a way to expedite this somehow. So what is proposed in this figure, and this is not the current configuration, this was an initial configuration. We have since, and I'll try to show you the final version, we have since found that this was not optimal. But the idea is to leverage sensors into our DAC and then build a series of microprocessors to do the data processing for us. Based on what we learn through materials testing, based on what we learn by interacting directly with the material, we can code this system to be able to do that analysis for us and ultimately compare it to models. Why? That's one of the easiest ways to do prediction. If we can get a nice connection between the physical and the model, we now have a way to help improve our data sets, to help really probe and turn knobs individually in a model that you can't necessarily do experimentally. Things aren't always decoupled experimentally, as much as we may want them to be. So let's talk about some of these examples. First, the microstructure, as I've been emphasizing, is key to the mechanical response. How do we know this? Well, here's an example of a magnesium single crystal compressed. First, along the C-axis, so compressing it in one direction, and then compressing the same material in a different direction. Just by looking at the color maps, the DIC results, we see a huge difference in the way the material is responding. We see a difference in the mechanical behavior as well, but that mechanical behavior comes directly from what the damage mechanisms are. That comes directly from the crystal orientation. Depending how we manufacture, we can achieve preferential directions in one of these orientations or the other. If we do, we end up with a material that has preferential orientation and ultimately has different mechanical behavior. Makes sense. We can then monitor this and not just look at the difference in mechanical behavior, but look at trends in non-destructive testing. So these dots that you see in both cases are acoustic emission trends. In both cases, we're seeing, generally speaking, that if you look at this, we have material here. We have energy in both cases that spike around yield, but there's a very different amount of activity going on. Why? The reason is that the microstructure is evolving differently. The case here where we have the predominantly red orientation, which corresponds to the situation, we have predominantly dislocation type motions leading to failure. In the case on the left, the ND samples, we actually induce a mechanism called twinning. So we're causing a specific damage mechanism to happen to change the behavior. Usually we like to avoid these twins in order to ensure we don't nucleate cracks and fatigue. So knowing this, we can actually choose material orientations and subsequently choose material manufacturing processes that can give us that preferential direction. We can also affect its composition by adding to magnesium. In this case, we're going to go with an alloy of AZ31, and we're going to add additional elements in order to change the microstructure again to produce different results. Notice, though, that by adding and altering the elements with very small amounts, we're not drastically changing the mechanical behavior. Not nearly as much as the orientation was in this case. We can do the same kind of a thing looking at a different alloy. In this case, I'm focusing on this one because I've done some exploration of additive manufacturing for an aluminum alloy as well. And this gives us a nice analogous to the kind of mechanisms that might happen that we can look for in the additive realm. We take this, just to give an idea, this is the microstructure of the whole sample. I'm actually only monitoring this small region in here. So the spacing between each of these dots is on the order of 50 microns. And I'm looking for what's going to happen to these particles that result from the process. So this particular alloy is aluminum 2024, precipitate hardened, which has larger particles that form during the process itself. These larger particles are damaged nucleation zones, things we need to be aware of. Just so you're aware, we went through, we did validate what each of these particles is made of, and there's a reason for that. We also went through and just characterized what the structure looked like to begin with, just so you have an idea. The red are the particles, the green small dots that are very hard to see are voids. So this particular material was hot rolled, and we achieved a material that has very low voids, very small amount, and not too many particles. And we characterized how they're distributed in space. So in this process, we achieved a material that has particles fairly uniformly distributed. The particles in this case are represented by the blue histograms. And we have voids that are not quite uniformly distributed. They seem to be predominantly existing below the surface in the normal direction. So as we rolled, we essentially affected how the voids on the surface are in comparison to the ones below the surface. That's going to change the way it behaves. Two, if we look into this, we want to keep in mind that not only do we have the voids that are different, but we have different particles that exist within here. And as we process this, as we apply loads to this, and anytime you think about processing, there's going to be loads applied, mechanical or thermal. Either way, it leads to stress concentrations, strain concentrations, and damage if we're not careful. This is an example of some of the particles that exist, 3 of which broke, 1 didn't. The copper-rich particles seem to be stronger. That's useful information. But the real takeaway here is if we want to think about this material is made of aluminum, and these particles are essentially embedded in it. It's basically like a composite. And if we take and map the material properties around this area, you will see that there are concentrations of elastic modulus and hardness that are different from the surrounding aluminum. This difference in mechanical properties is going to cause stress and strain concentrations and lead to failure. Can we detect that? Well, first, let's figure out, to some extent, what we might be interested in detecting. So to do that, we're going to do some modeling. What you see here, in addition to the details of the model, is an example of a crystal plasticity finite element simulation that has a single crystal, the green, of aluminum, with a particle embedded in it. The properties of that particle, in this case we're assuming perfectly round, is altered to simulate the properties you would expect from an aluminum 7 copper 2 iron particle versus aluminum copper magnesium versus just aluminum copper. What we notice is that for the most part, if we look at the bottom row, we're looking at the strain. There's not any obvious differences. It might be a little bit higher concentrations in the case of the aluminum copper in the area around the particle. But we notice the stress in these particles is significantly different. So we know these particles are going to play a role, and that some of these particles are going to carry higher loads than others. So the question is, are some of these critical to its behavior? If we also take into account not just the difference in properties of the particles, but the crystal orientation. So in this case, we're changing the aluminum to be 111 orientation versus 100 orientation, hard versus soft. You'll notice that the concentration of these red dots indicate where fracture is going to happen, at least where we think it's going to happen. In this case, in the hard orientation, we expect the fracture to actually occur in the particle itself. So the particle, the reinforcement is going to fracture. In the case of the soft grain, actually the aluminum or the bonding between the aluminum and the particle should be what fails. So we have two mechanisms. If we want to know that these two mechanisms can change the behavior, and these are what's a concern, can we detect them? Can we detect one? Ideally both, but can we detect at least one? Can we do so considering the fact that in reality, a particle does not usually sit just in a single grain. Many times they're on boundaries. And this is just a quick simulation to show you the concept that if we take a grain structure with different crystal orientations and we strain it, the stress and the strain is not going to evolve uniformly. It's going to concentrate in the different grains because of the preferential orientation. Given all of this information, we want to be able to detect that these kinds of things are happening at this scale if we want to be able to control them. So, can we do that? Let's take some of these tools that we talked about before and let's see if they can actually show us what we think is going to happen. Is there that connection between that model and the experiment? So, first, the results of DIC. Looking at this, we do see that there's a very large amount of variation in strain buildups. If we zoom into these concentrations, and a number of these boxes are doing just that, you will notice that in all of these cases, there is a particle. The white ellipse here shows the outline roughly of where the particles exist. There is a particle involved in all of these concentrations. Some have fractures. If we zoom in on one in particular, we can actually start to map what's happening to this material. How is this behaving? How is the bond between the particle and the aluminum operating? Is it holding? Is this fracturing from the particle? Why is this particle fracturing? If we can answer these questions, we now have the potential of altering the structure in a way that's preferential to the material behavior we want. These lines that you see here, just to illustrate the power of DIC, each one of these lines represents a location where a virtual extensometer was placed. And what we see is when we initially load, the whole area behaves the same. So in the elastic regime, our thought process that the material is behaving isotropically is fairly accurate. But as we continue to load and we start to get into plasticity in some regions, we start to notice that there's a difference in behavior at different locations of this material. Not only that, but in some cases, we start to get nonlinearity. So we know there is an effect. There's an effect of this particle on the way the strain is evolving. What can we do then in order to minimize that effect? How can we change that? Can we come up with a method to reduce the size of these particles, to reduce the concentrations that are resulted from these? Well, the question becomes, can we actually detect these? Do I need to actually image this at the microscale every single time if I want to be able to figure out if it's getting any better? Short answer is no. What I'm showing here is an example of indenting directly onto a particle to cause a fracture versus indenting on the aluminum. The reason I'm showing this is I monitored acoustic emission, energy release from these processes. When we fracture the particle, we get a very clear burst energy release. When we do the aluminum, we don't. That means if I want to reduce these fractured particles, acoustic emission on its own is a valid way to determine if my processing parameter changes have achieved my desired result. If I get fewer of these hits of these signals, then I'm fracturing fewer particles. Makes life really easy. We can then extend that and use just that to talk about other properties. In this case, fatigue, low cycle fatigue in this case. Looking at this waveform, we can take it, we can characterize it. We can say it has high amplitude. We can say it has high frequency, about 500, between 500 and 600 kilohertz. We can figure all of these things out and plot them. And what we see is that if you look, those signals are an early mechanism. That's an early defect mechanism. That's a mechanism that initiates crack growth. That's a mechanism that can exist under surprisingly low loads and can alter the behavior, which means it's something that we might want to be aware of as we're processing materials to use. are we fracturing a lot of these particles during our processing that's going to alter the behavior of the material? What we also see as validation is that these particles are indeed fracturing. And then we do see that when we start to reduce the number of these signals, that we actually have cracks starting to grow in the aluminum on the surface. So yay, our AE is reliably telling us about microscale damage mechanisms. That's good. It's not metal specific. The point of showing this is the use and the power of the methods in order to improve material properties. So this particular example was a question that DuPont came to us with and said, hey, we have this material. It behaves in a certain way, this red line. We're trying to make it more damage tolerant. Can we characterize what's happening to this material so that we can make informed decisions about how to alter the structure? So what we did was take this, we applied the load, we did this first at this scale in order to prove that there isn't any significant out of plane motion, to prove that microscale investigation can work. Once we do that, we can then bridge the microstructure, full three-dimensional microstructure, to how the material fails based on the non-destructive testing. This is just with DIC, not even considering acoustic emission yet. And it's very clear that in the case of the first material, we have large particles and it's very brittle. In the case of the second material, we have small particles. Both of these materials are made from the same things. The only difference is the size of the particle. And we have much more ductile failure. Instead of particles fracturing, the material is growing around the particle. It's growing through the polymer. And AE shows that beautifully. Those where the particles fracture has a lot of activity going on. Those that don't, where you have the polymer failure, has very little acoustic activity. Knowing this, we have the possibility now of saying, well, clearly the smaller the particle, the more ductile we become. But we do so at the sacrifice of the load. We change the load. Can we alter these things? And just to show you exactly what's happening, this is what you see here. This, as you step through it, through the fractures, you barely even see the fractures here. They're all extremely small. What that means is the way this material is set up, the way this was it developed, is that instead of having a single crack that grows across the whole thing, the particles that are placed in here are of a size that actually impedes growth. It grows to a certain size and stops, and another location nucleates. As a result, we get a much better elongation behavior. Same thing can be done. Instead of at the microscale, we can move up to the mesoscale, to the macro scale. And the point of showing you this is just to indicate, again, the reason we're talking about AE and DIC together is that this material is made up of a layered composite structure. If we want to understand how the layering is effective in causing changes, we have to know what's happening in the middle of the material. DIC is only going to tell me whichever surface I'm looking at. It's very useful, very helpful for that. It shows me that you have debond from fiber and polymer, but you have no idea what's happening on any of the other layers. And so with acoustic emission, we could start to do this and look at the fact that we have activation of different mechanisms at different times. Now we can start to piece together that this material fails by matrix cracking. Then you have the debond on the fibers on the surface. And then eventually, much later, you have fibers themselves starting to fail. Very helpful. Now, that's nice, but that's a lot of data and very hard to figure that out. And it's a case-by-case situation. That means we need some way of dealing with this in order to be able to make this useful for in-situ processes. If we want to be able to monitor the manufacturing process itself, we have to be able to do it in situ and process the data fast. That's where machine learning comes in. If we do all of this background work, we can start to piece together based on the microstructure, based on the NDE, based on various investigations we're doing, very controlled experiments and combinations with modeling. We can identify the difference between final fracture, damage initiation, and noise. From there, we now have the chance of saying, okay, if I'm doing a process, if I'm manufacturing this, I want to see if I induce a crack during my process. Well, now I know what a crack looks like. Now I have a chance during the process of being able to detect that it happened and tell somebody that it happened. This can be applied both in monotonic and fatigue situations. Very helpful. Excuse me. This is not the only option. There are methods of doing basic outlier analysis as opposed to very detailed clusters. If you do outlier analysis, it gives you an idea of whether it's damage or not. If we do something like this, not only can we say if it's damage or not, but we actually have a chance of saying what kind of damage. Can that damage be fixed? Can that damage cause this thing to have to be removed from operation? Or is that actually just the start of nucleation and we just have to watch this more closely? So, how do we take this further? What advances in these AE tools are we doing to allow us to actually monitor these processes? First, non-contact AE, in particular, laser AE. So there's a number of options. If you think about it, if you have to make contact with a material, if you touch the material, if you put glue on the material, if you add a sensor to the material, it's going to change its behavior. So can we monitor what's happening without actually making contact? That's the question. Short answer is yes. So this was developed initially for Air Force research labs for trying to monitor fatigue crack initiation in a what they call a free vibration setup. So the premise from this is that your sample is held from fishing line and the load is applied by a solenoid to induce bending, mode 1 bending. And the question is, can we detect when cracks nucleate in this? This is a very thin film sample. So we're investigating this predominantly for turbine blade applications. If we make contact with this, it's not going to be in mode 1 bending anymore. It's not going to fail the right way. We're not going to see what the material is doing. We're going to see what the structure is doing, what the system with the sensor combined is doing. So we want to try to see whether or not we can do this with a laser. What we're seeing here is two approaches to non-destructive evaluation with one sensor. The top monitors the resonant frequency. We're vibrating this at the theoretical resonant frequency of the material. Once a crack grows long enough, the amplitude should drop. The bottom is acoustic emission. All of this comes from the same raw signal, except filtered. So we can see very clearly that embedded within this frequency, within this vibration, is this piece of information. We can also see the frequency that I'm applying here. There's an additional little error here with these bumps at the top, just to show you how powerful this can be. That was a fractured grip. We were monitoring nowhere near the grip, yet we knew the grip was fractured. We're exploring other ways of doing this. How can we get useful information out of these waveforms without having to go through the detail of doing complex filters, extracting each one of these waveforms, calculating all the features for those waveforms? That takes time. It makes it impractical if we're trying to detect damage. We're trying to detect it in a time that we can actually do something about it. That's a problem. If we're doing an additive process, we see a fracture happen on the surface that we just built, we'd like to be able to go back and try to patch that before we do the next surface. If we don't start exploring new ways of dealing with this data, we're not going to be able to do that in a timely manner in order to be able to correct it well. And what we're exploring here is different spaces to do this analysis. Frequency space, temporal space, compared to the load data, and see how things go. 2, ex situ data coupling. Ultimately, we want to do in situ. But if we're going to do that in situ, we have to be able to couple the data together. To do it in situ, we need to know what we're supposed to connect. That means experimentation offline. What are we looking for? So in this particular situation, we're trying to develop a coal-based polymer composite material for structural applications. This particular one is coal particles embedded in HDPE. The top and the bottom show you the result of injection molding this material. The top sample corresponds to these low load curves. The bottom sample corresponds to the high load curves. Ultimately, we like the high load curves. We would like those. But if we're not careful about how we're processing this, it's very easy to end up with these pores. And they're going to drastically change the behavior. So we're exploring this from two aspects. First, we're trying to understand what effect this has on the material, why this is happening from a chemical, from a manufacturing process perspective, and can we adjust it? And then two, can we monitor during the process itself to see whether or not this happened? Right now, the only way we know is either put it into an X-ray system or break it and see if there's a pore in it. So can we monitor the process to determine that this has happened in order to make some adjustments, to make a correction, to alter something to fix that? Short answer is if we look at the acoustic emission trends for pure polymer versus the composite materials, you'll notice that there is similarities, but large differences. All of them have these burst signals, low duration and rise time, but this material has significantly more activity. So the question becomes, why is that? What is causing this to send so much energy as it's failing that these others don't have? This is very similar to the work we did with the DuPont, and what we found was these two composite materials made with the same parameters, with the same pulse particle size, same weight percents, have very different mechanisms. The pit 8 fractures brittly. Particles fracture. PRB doesn't. What I want to make clear is pit 8 and PRB are both coal. Theoretically, they're the same thing. They came from different sources. So the manufacturing processes we use for one of these sources clearly is not working for the other. So what can we do to fix that? That is a question that we are still trying to answer. We don't fully understand yet what exactly is causing the difference between these two. We have some hypotheses. We think it has something to do with the way the heat is being placed into this material and some volatiles that are coming out of the PRB that weaken its bond to the polymer, but we're not sure. So we have to find a way to figure that out. And if we can figure that out, now we can make adjustments. We can inform how to manufacture this better. Just to emphasize that, so you can see, instead of just looking at this kind of a waveform, we can overlay it with a load curve so you can see a little bit better what I'm talking about as far as how this material is so much different than the others. Do that, we want to try to do this kind of a coupling, the manufacturing. We want to do this during the physical testing to see what's happening. So I alluded to this before. We started playing with an IoT concept in order to do this analysis. So this left schematic is our current data flow process. We take the raw data, we filter it, we place that into a hard drive for storage because we want to make sure we don't lose data at this point. While that's happening, the hard drive can be reading into other systems that can do Fourier transforms, that can identify peaks, that can do different plotting, that can potentially do outlier analysis. We can keep adding to this flow, but this is the current scheme. This is done using a cluster of microprocessors. In our case, we're actually implementing Raspberry Pis. The premise is this external hard drive is our link between our data source and the processing itself. So as the data is collected, it's periodically dumped into this drive to be immediately processed. We're exploring two possibilities here. One is to continue this kind of a dump process approach. For systems that we're talking structural health monitoring over long periods of time, that makes sense. If we're talking about manufacturing processes, that makes less sense. Because by the time you've processed one of the data dumps, it's probably too late to fix it. For that, what we're proposing is altering this master node to be able to take the data in directly and then save it. The problem is making sure that the processing nodes and our data acquisition systems are able to communicate with each other at a high enough rate. So we're exploring different options for that now. Once we have that, the rest of this is just a series of nodes, basically set up the same way you would set up a cluster for any other type of computing. And we can tell and delegate each one of these nodes to do a specific process. So node 1 could do the low pass filter. Node 2 could do the high pass filter. Node 3 could be doing peak identification. But the benefit here is I can add as many nodes as I want. And if for some reason node 3 fails, I can have a backup and say node 4, which was just sitting there, replace node 3. So you never lose processing time. And just to give you an idea, this is ultimately what it looks like. Right now, with just a basic setup, we're looking at right now 5 processors, the external drive, and then data collection offline. What can we do with this? This is an example of us monitoring, in this case, an extrusion process. We're extruding aluminum wire. The intention behind doing this particular process is we're trying to improve the conductivity of that particular wire. So what you see here is the extrusion pressure in red, the ram displacement in black, and the acoustic emission in blue. On the right-hand side, we also have acoustic emission activity in red and green, just to give you a couple of different ways of seeing what's happening. You'll notice everything is fairly consistent. There's nothing out of the ordinary. You don't notice anything very unique during any of this process, even during the initiation of force. Nothing really changes much there. Until this purple box region. Suddenly, there's a lot of AE activity going on. Has a lot of energy. So the question is, what happened during this process that caused that change? We don't really notice any difference in the force that's being applied. We don't notice anything in our parameters that we're using to manufacture, but something changed. And we actually look at these waveforms. We notice that early on, we have this very consistent, repetitive, machine noise almost looking wave. And then later, with these here, we have these very burst ones that I said were fractures that look a lot like fracture. The frequency is lower, but they're sudden. So it's something happened suddenly. We don't know what it is just from this. But what we do know is that if we plot the electrical conductivity as a function of material length, and we plot the AE as a function of the material length, whatever caused these signals also caused a change and an improvement in the electrical conductivity. So this section here between 20 and 60 inches in length is a consistent process. Up to 20 inches in length is the initiation of the material. So that usually is going to get cut off. And this end point usually is the end of the material gets cut off. So something changed at the end that causes us to have better conductivity. If we can understand what that is, perhaps we can find a way to replicate it earlier. So we improve the electrical conductivity overall over this entire wire. Now, the one I spend most of my life on, NDE for additive manufacturing. I mentioned before I went through a detail of that aluminum material, and I did it for this reason. We were trying to understand additive properties, additive parameters on how the material responds. So we call this nominal, 50% reduced, and you'll see there's also a 25% reduced. Nominal is what literature proposes as the optimum manufacturing parameters for aluminum, silicon 10, magnesium. 50% reduction in power means we took the laser power and we just cut it in half. And we wanted to see what would happen. To give you an idea, starting with nominal, 25% reduced power, 50% reduced power, we have less material bonding. We have more pores, more lack of fusion defects. Makes sense. What we also see is a significant change in how the material fails. The properties are very different. In nominal, we have very good plasticity in zones. In 50% reduced, we don't. It basically yields and breaks. What was interesting was the fact that you have so much more AE activity in the 50%. If you compare the trends, you look at it in terms of amplitude, you look at it in terms of all of these, there's a lot of comparable. Amplitude's about the same. Energy is very different between the two materials. Rise time's about the same. Duration's pretty much the same, though you do see a difference in the mean. Peak frequency is different. Why do we have these different mechanisms? What's causing that? And how do we tie that back to laser power? Well, we can throw everything we have at this, X-ray analysis, acoustic emission, look at the different AE features we see, and we notice there are some similarities between these two materials, but there are some differences. And what's essentially happening is, in the case of the optimum condition, optimum configuration, there is a single weak point that is dominating its behavior. So while it's optimum, you have one primary location that's going to fail. Whereas in the case of non-optimum, you have a lot of nucleation zones. You have a lot of voids that could lead to failure. And what's happening is a number of them are fracturing. So you have many locations cracks are growing and stopping as they interact with other voids. That's actually a process with arresting the crack behavior that could be useful if we can figure out a way to locate these as we're building. Can we control where they're placed, their size, their shape? That leads me into one of the processes we're working on now. And in this particular case, what we're trying to achieve here is we're trying to use ultrasound to change the grain structure of the material during a 3D print. And ideally, we will be monitoring this to see if we're being successful live. So just by looking at this, we have two samples, one ultrasound on and off. Both of these were built the same way. The lower part, the ultrasound was on. The upper part, it was off. The middle one, the one on the left, was right on top of the transducer that was inducing the ultrasound. The one on the right was a distance away. So we're showing that the method we're proposing is very localized response, which can be very useful if we want to start moving into a concept of architectured materials, functionally graded materials. The fact that we can target where the effect is very critical. When we turn it off, when we're directly on it, we do see a change in surface porosity. Once we polish this down past the surface into this base part of the material itself, we don't observe any obvious real changes in porosity behavior. There's a few pores here and there, and it seems fairly consistent across the material. We're in the process of now of doing an EBSD scan to see if we actually achieved the change in the grain structure. So what should be happening is with the grain structure, with our ultrasound off, we have something that looks like this. With it on, we refine it. So the properties in this region are going to be different than the regions around it. That's the premise. It's been proven to work for a very small scale build, for a build that occurs directly on a sonotrode. What we're hoping to achieve with this methodology that we're doing here is to expand this, to be able to achieve this kind of grain refinement on an actual component, something that's significantly larger than an inch across. So we're actually trying to achieve this on currently a 6-inch build plate, and we're in talks with the company that makes the 3D printer to transfer this up once we get confirmation it works to a 24-inch build plate, and start to explore what do we need to do to make sure that we can actually scale this up to make it useful for industry. So just to tie things and conclude, and hopefully will be a bunch of questions as we go from here. The basic conclusion that we draw here is if we want to understand material behavior, if we want to affect the material behavior, we have to go from the micro scale to the macro scale. We have to couple these behaviors and do so leveraging both experiments and computations in order to truly understand what those process parameters are, what effect they actually have on the material, and how they interact with others. And if possible, find a way to combine this all so that we can monitor the manufacturing process as the material is being made, so that we can then either at least inform when there's a defect, so it can be inspected in more detail or removed, or ideally inform that a defect has occurred in a timely enough manner that we can go back and fix it. And that is where I will leave it. And hopefully you guys will have some questions that we can discuss some things.
Thank you for the nice presentation. That was very interesting and informative. I appreciate it. Anyone, any question? So let me start. Okay, go ahead, Dr.
Oh, okay. Yeah. So yeah, very good presentation. That's great information. That very interesting talk. I guess I'll leave time for other people, but I just maybe one quick question here is what you just mentioned. You had an ultrasound on and off. If you can go back to that slide.
Yep.
So so my understanding is that ultrasound goes from the bottom, right? Because that's the field direction. So assuming this is kind of powder layer by layer based process. So when the ultrasound, I guess when you show this the section below this green line, that means this structure is basically it's starting to solidify each layer by layer during this process, but the ultrasound is continue on that will continue to propagate, and but you see like more voids, those like towards we're getting closer to the blue line, which is where the I guess the ultrasound get less intense. So then when you moving on above the green line, that's where you had ultrasound completely off. Right?
Correct.
Okay, I see.
Yep.
Yeah,
and
just want to clarify.
Yep. And what we're trying to understand here is, I should make a clarification that we ran into an issue. This is the first build we ever did with this process. And what we found out is we were not able to achieve the intensity of ultrasound that we ultimately knew we needed to be able to do any sizable part. So part of this experiment was to try to see how far up it would go before we started to lose the effect of the ultrasound, knowing that we're not quite to the settings we want to be yet. And we're troubleshooting what happened because we were able to basically, our goal is 60 volts going into the transducer. We were achieving 23, which should have been enough to do the result on the lab bench. Once we transferred it into the AM machine, we were discovering that we weren't even able to achieve the 23 anymore. We were getting something more like 18. So it's on the borderline of what's enough to cause an effect.
Okay. Yeah, very interesting. It's and the one on the right side, that is without any ultrasound, is that?
So this was part of the ultrasound was technically doing the same thing, but the transducer we used was about the size, so the base of this is about the width of the transducer. The one on the right was sitting about 3 inches away from the transducer. So we were trying to see whether or not that transducer would reach that far. And the answer clearly is no.
I see. Okay, thank you. Yeah, thank you. Yeah. And also, if I can just remind everybody, please complete the survey, provide feedback using the link in the chat box. Okay, thank you. Yeah.
One question that I have, I know that you are talking about the micro scale, and the thing is that I'm wondering if we go down to even to angstrom scale or the nano scale. So the thing is that it comes to my mind that the size would be comparable with the structure of the material. What would change in the nature of this computation or research you envision when you go down to that size?
Yes. So there is a concern between bulk behavior, thin film behavior, and non-representative behavior, because as you scale up, obviously you're going to have neighbors, nearest neighbors, second nearest neighbors that all start to affect things. And that's part of why I propose the experimental approach, because we can layer by an experimental computational, we can layer by layer add those effects in. So what I should show, let me go back, assuming my gonna work. This model I originally showed you, which I'm hoping to continue pick up with this a little bit more. Where is it? This guy was a very quick approximation, not considering nearest neighbors. This was only the effect of the crystal structure itself. We didn't talk about the neighbor or the next one. So part of the exploration, and that's why I was showing you this, was even this model that we did here was a single grain, not considering the effect of how a neighboring grain would change the strain that comes into here, which will affect this behavior. But the trick behind a lot of the modeling we're doing is trying to isolate the energy release from a given mechanism, from a given concept. So by doing it this way, we're able to focus and force the fracture and see what the effect of one parameter is. What we obviously will need to do is start to add in the others. And as we go down lower in scale, this challenge is going to get worse. Every time you drop a scale, there are many parameters that come together that are required in order for you to predict what's going to happen at the next scale up. And this is the challenge of multi-scale modeling that's always been in existence, and it's true of experimental as well. As we go down in scale, we're going to lose bulk behavior. But we will be able to probe individual mechanisms, individual parameters, and make that connection to what the NDE is. For example, when I did my NDE at the microscale with the particle or nano indentation, that is a very singular particle response, but its wave propagation that was produced was the same because I used the same sensor for both scales. Does that make sense?
That makes sense. Yeah, I expected that's difficulty that you mentioned. Yes, that's true. The purpose of the question was that with Dr. Shu, we are looking at atomic layer deposition. So so that's your expert, and you know that we are talking about that angstrom or nanoscales. So here's the thing. I'm thinking if at each layer of deposition at the end of each cycle, if we knew there is a crack or there is a defect on the structure, then what is the remedy? What is your solution for that?
Yep. So that's part of what we're trying to figure out. So the method that we're proposing for our powder bed fusion right now, which is it's not necessarily the most optimum, but it's mostly trying to be a proof of concept, is that if we detect a crack happened, we're going to have to make the assumption that it happened on the most recent layer. That may not be true. It may have actually happened a couple layers down based on the thermal history. We're working on a way of trying to detect that, leveraging the ultrasound transducer on the bottom because it can send, and the AE sensor on the top to try to see if we can't find the location. That's a little bit further down the line. But for right now, what we're going to do is assume that it is at least on that surface. And basically, we're going to pretend the laser hadn't fired on that surface. And we're going to go back. We're going to remelt that layer. Ideally, altering the laser parameters. If we can determine if it was a lack of fusion, we want to alter the parameters in order to maybe go a little bit slower to try to hit that region better. If it was stress cracking that the thermal cooled too fast and maybe we moved across it too fast or we held it too long, that's going to be the question, is trying to figure out what it was that caused the fracture so that we can go back and fix it. Because if we don't know, it won't solve it. But the initial proof that this could work is us detecting a crack happened and then going back and repeating the layer to show that we have that communication. And as long as we can find a way to detect, and maybe this means we bring in a thermal camera as well. Maybe it means we bring in ultrasonics as opposed to just acoustic emission. There's a number of options: thermal imaging, regular imaging. Combine all of them. At this point, we don't know what we're going to need to be able to determine what type of failure it was to pinpoint the exact remedy that we would need. But if we can prove it works with one of these, now we can start talking about multi-physics data fusion to try to figure out what is the defect, what actually happened, and target the correction instead of just doing a general remelting.
Yeah, that totally makes sense. So my assumption is that it's your solution is highly dependent on the process as well, because if you're talking about the CVD, the temperature already is very high, and that temperature makes the situation worsen because makes the crack faster to grow. Okay, that's very challenging and interesting. Really,
it is. It is very challenging. That's why I spent so much of this presentation talking about the microstructure, because that's a level that we can definitely monitor during these processes. As we go to smaller and smaller scales, we're limited by technology. Do we have the technology to actually be able to monitor it? There's a limit to what the sensors can detect. And that's another reason I moved from the pico sensor to starting to use the lasers more. The laser vibrometer I'm using is extremely sensitive, way more sensitive than the pico sensor that I've been using. I'm in the process of getting the data for that so we can actually show you exactly how much more sensitive it is. And that's a good thing and a bad thing, because we're doing this work with AFRL, and they gave us the data, and their response was, it's too sensitive. They had to stop people from walking around the machine during the testing because they could detect footsteps 5 feet away. Which is nice because it's sensitive, but it's a problem because that's contamination. And until we know what we're looking for, we're going to have a hard time setting up that signal processing to eliminate the contamination and focus only on what we're talking about. That particular material is Ti-64. We don't have as much data on Ti-64. If this was aluminum, I would have said, yeah, just leave it in there. We can probably get rid of it and be fine. You've seen how much data I have on aluminum. But anytime you go to a new material, you have to build the database. And if you think about it, it's a machine learning challenge that exists. And anytime you're talking manufacturing materials, is people want to call it big data, but it's not. It's big data theoretically, but right now it's very sparse. We don't have enough fill to be able to really use it. So how do we solve that? Which again comes back to the fact, if we use a laser, we can actually do a one-to-one comparison with models. We don't need a transfer function. We don't need to simulate the sensor as well. We just need to simulate what the surface is doing.
Yeah, I have questions regarding you mentioned the material. So
yes,
the powder, did you try to characterize this property, like size distribution, or is this off the shelf from the vendor? That's pretty big impact.
Yeah. For our initial build, it was off the shelf to get printing and get things working. My student literally actually about an hour before we had this presentation showed me the image of the powder where he's starting to characterize the particle size distribution. So we're in the process of doing that, but we don't have those results yet. We do know that just qualitatively, there's a huge range in particle size.
Oh, yeah.
Which we were not quite expecting. So
yeah, I read learned somewhere that there's a big impact and big size differences in different powder you can get even with the same manufacturer. The size variation is quite big. So yeah.
Part of what we're hoping with this ultrasound too, and we're not sure if it's going to work, is that by introducing the ultrasound, by agitating the system as we're building it, so you have energy coming from both areas, that we might be able to help reduce some of the particle size effects on the prints. We don't know if that's actually going to happen, but we're hoping that's going to be a byproduct.
Okay. Thanks.
The next step would actually be to see if we can actually use the same concept for recycled powder.
So, go ahead. Sorry.
I would say that the idea behind it would be that by improving the quality of the structure in a good powder, if we use a recycled powder, if we still get some improved quality, we might be on comparable to what current additive is at its best. So we're hoping that both will lift up a step by introducing this agitation, by introducing this additional energy source that's mechanical rather than thermal.
So you hope that in future this technology is integrated into the machine, and at the simultaneously that's very interesting.
The project is actually SBIR phase 1 right now funded by Defense Logistics Agency. And so we're in the process of building the phase 2 proposal. We need to get the rest of these results in and prove that it is working not just on porosity, but as they want the grain size. They're ultimately interested in functionally graded material. They want to say, hey, if we use this, can we control the location and the frequency and the intensity so that we can say that if this material is going to fail, we can build it so that it's guaranteed it's going to fail in X location. And so if we're doing maintenance, we only have to monitor X location as opposed to the whole thing. That's what their ultimate goal is. We're a little bit away from that yet, but that's kind of the direction we're trying to go with it, while thinking about what else we might be able to do in that process along the way.
That's very interesting, especially when you say SBIR. That's the mixture of the real application and the science. That's very, very interesting. So any questions, other colleagues, students, any questions? And students specifically, don't be shy. So we are here to just have fun. So please ask any question that you have.
How are you coupling the ultrasound probe with the AM material?
Yeah, that's one thing. I'll give you the information. I did not get clearance to show you the figure, so hopefully you can follow my description here. I don't actually have them on me, so you can think about it. Basically, if you think about the way a build plate is typically set up in a powder bed fusion, you have your plate itself that you're building on, and then below that you have your support plate, your understructure that is balancing everything that you attach your plate on top of. What we're basically doing is sandwiching between that the transducer. So we're squishing that between the two, and then we're isolating it with foam in order to get a balance, because if you have a single transducer in the center, it's hard to get it balanced. So we're using a foam structure to, one, keep powder from falling underneath, and two, help us balance the plate, but allow enough give that the plate itself can actually vibrate. Because if the energy is not going into the plate, and the energy is not transferring through into the powder, it's a problem. The way it's been done in the past is using a sonotrode, so the entire system is vibrating. We're trying to make something that could be a standalone system that you can simply add to an additive machine that can do it. We have other thoughts in the works about how we can do things a little more complex, particularly talking with EOS and open additive companies about that, are talking about how we can integrate this directly into their machine where we have more control. But for right now, since we are operating on our own machine, if we break it, that's a problem. We are building basically a sandwich plate that we just set on top and acts as our build plate. Hopefully that makes sense.
Okay.
And we're using a high temperature vacuum grease essentially as the couplant to the plate.
So the system you have is customized, like, or is commercial?
For the additive, additive machine we have.
Yeah.
We have we have an open additive. They're called Panda now. We have a beta. So the second machine they ever built is the one that we have, which means it's very finicky. So I classify it as custom.
Okay.
But it's the precursor to a commercially available machine. The build plates and chambers and all of that are the same. The laser controls and the wiring scheme is a mess in ours and much cleaner in the commercial version. But the processing, the parameters, the basic operation are all the same.
Okay.
Any other question? So, I have a question. Sorry.
For the acoustic emission, you're doing a C-scan on wherever the area. Is that correct?
So
You're
for
doing
acoustic,
yeah,
for acoustic emission, you don't have to you don't have to think about scanning. For acoustic emission, you're placing a sensor in one location, and what you're thinking about is the easiest way I can analogize this to is think about how earthquakes are detected. You have a transducer in a given location. The wave travels from its source to that transducer to cause it to move, and thus you know you have the earthquake. AE is exactly the same thing on a much smaller scale. So we place the sensor in one location, ideally as central to where the damage is probably going to be as possible, because the farther it travels, the weaker the wave's going to get. So if you can place it near the source, that's preferred. But so long as you have it in a range that's detectable, you're fine. And since we're talking mostly metals or even composites that have fiber, waves can travel pretty far. Make sense?
Good.
Any other question? So I would like to thank the time that we spent. That was very, very interesting. I think we definitely continue our work with you. We have a very advanced facility. I hope that it was not COVID. We could give a tour to you and to the lab that Dr. is a director of the advanced manufacturing 3D printing center. But we definitely will be in touch with you, and hopefully we start a collaboration. And good luck with your phase 2 SPIR.
Thank you. That sounds wonderful. Yeah, the results of that one would have been farther without COVID. So trust me, I understand the COVID challenges.
Yeah, that's. But definitely, we will be in touch with you, and good luck.
All right, thank you.
Yeah.
Thank you.
Take care, guys.
Thank you very much.
Freshman students, please migrate to the class WebEx. Thank you.
Thank you.
Thank you.